looking at the last rule of derivatives that we're learning for this chapter, which is derivative of logarithms. So we want to kind of do a little bit of review from algebra. First of all, what is a logarithm? And so I pulled up this picture here, and logarithms, we would write it as log. We would have this base, so it's like a subscript of where you have log, and we say of b, usually there are parentheses here. All these are exponentials. So basically what you're trying to think of, what is my exponent? So when you're thinking of logs, you're thinking, what is my exponent of my base that will get me this b value? So let's just write it out real quick. So log base, I usually put base b instead of a. Let me just write it this way. Base b of x equals y. This is equivalent, the same thing as saying, what do I take my base? My answer is my exponent. So what am I going to raise b to get back whatever I'm taking the log of x? We have to have a few stipulations here because our base always has to be greater than 0. It has to be a positive number. And if it was negative, when you're raising it to different powers, it's going to bounce back and forth between positive and negatives, and that's not an exponential function. And so b has to be greater than 0, our base. B can't be 1. And then for our domain, what we're taking the log of, that always has to be greater than 0. The key thing is to know this here, that all we're doing when we're taking a log base b of something, we're looking at what is the exponent of that base that would give us that something. And so here's the example. If you have log base 3 of 81, you're thinking to yourself, 3 to what power is 81? And so 3 raised to the 4th power, if you multiply 3 out 4 times, 3 times 3 times 3 times 3, you would get back 81. So the answer is 4. Maybe do another quick example. Let's say you had log base square root of 2 of 2. And we want to know, what is that equal to? Let's say it's y. So this is saying, what am I going to raise? Maybe this was a little harder one than I wanted. What am I going to raise root 2 to get back to? Well, there's a rule, we can do it, that says if we have the same base, b to the m equals b to the n, then our exponents have to equal each other. M has to equal n. And so we can manipulate both of these sides to look like each other. Let's first rewrite square root of 2 with an exponent. And so square root of 2, and we've been doing this when we were taking derivatives, when we had radicals, a lot of times we rewrote it so that it didn't have the radical anymore and put it in exponential form that's equivalent. So this is 2 raised to the 1/2 y equals 2. And this 2, right, is raised to the 1st power, it's just not shown. There's another rule that says if you have the same base, or not the same base, if you have a base raised to a power raised to another power, the rule was for exponentials, exponents is that you multiply. So b to the m times n power. So we could take this 1/2 times y power. So this would give us 2 to the 1/2 y equals 2 to the 1st. So now we've manipulated those bases to be the same. We can set our exponents to be equal to one another. So we have 1/2 y equals 1. I'm jumping ahead myself. And now we can get y by itself by multiplying both sides, clearing that fraction, by multiplying both sides by 2, or we can think of it as dividing both sides by 1/2, which we'd have to invert multiply, which would give us 2. So this would give us y equals 2. So what can I raise square root of 2 to get back to? Well, makes sense. If I square, right, 2, square the square root of 2, I do get back 2. So our answer is 2. Okay, so that's a quick refresher a little bit on what logarithms are. Those are inverse of our exponential function. A couple other things that you need to remember about logarithms. A lot of times we'll be working with natural logs. Natural logs are a lot easier than a log of a different base. Natural logs, ln of x equals y. This is the same thing as log base e of x equals y. So natural log rhythms, and then you reread it as L in. So a lot of times I write my L in like this, lowercase l, but sometimes students get confused. They'll tell me later on, multiple weeks later, that they thought that was a 1 and that's not a 1. So I'll try maybe to do it as a capital L. The other one, but we really a lot of times want to use natural log, would be log if it doesn't show a base. No base is shown, then it's known to be base 10. So 10 to what exponent would give you back x? Okay, so I just rewrote it or typed it again. Log base b of a, if this is equal to c, another just they're using different variables. We would take the base, our answer is the exponent. The exponent is equal to what we're taking the log of, a. Other things that can be helpful for us, we can take a complicated log and rewrite it as simpler logs. So there's your exponential rules. We've gone over those. I just posted those with this, but let's go over, there's rules of logs, how we can rewrite a log. So if you have a log of something times something, so in this case it says a times b, we can rewrite that as a sum of 2 logs. So if there's multiplication of whatever we're taking the log of, we can break it up as a log of the first factor, a, plus a log of the second factor, b. And if we have a log, and this can be any base, right now it's showing base 10. If we have log of division, so a divided by b, we can break that down as a difference of 2 logs, the log of the numerator minus the log of the denominator. Another thing that's helpful is if we have an exponent, we have a log a of some exponent b, we can take our exponent and we can bring it down front and write that as b times our log of a. These other ones it's just kind of weird that they're in here, but I'm just going to talk about them because I copied and pasted them. So this is saying x, right, raised to what power? And it's telling me negative a, which makes sense. This is going to give me back this, what we're taking the log of 1 over x to the a, right? And this is rules of exponents. I have a negative exponent, right? I bring it down to the denominator and make that exponent positive. I guess these are all correlated kind of with each other. And then this one is saying, if I have x, what do I raise x to? Well, I raise x to the 0 power to get back 1. Okay. So those are some rules of logarithms that we might pull in a little bit later to help us take derivatives of logs. Okay, so now let's figure out how to take the derivative of a log. And before we do that, one more quick reminder. We are gonna look at 3 and 4 today, but we have learned 1 and 2. And so differentiation of exponential and logarithmic functions, exponential functions, and their corresponding inverse functions. So I just mentioned that logs are just the inverse functions of our exponential functions, are called logarithmic functions, and they have the following differentiation formulas. So we found the easy one was if we have f of x equals e to the x, then our derivative of f of x is e to the x. A little more complicated one was if f of x is equal to some other base a raised to the x. We had to have our stipulations. A was positive, a didn't equal 1. The derivative we found was the natural log of whatever base we had, in this case a, times the original exponential function a to the x. So I want to derive how we're going to get the derivative of the natural log of x. So doing research the last few days, teaching this in the other class, my STEM class, I've noticed that there's at least 3 different ways to prove this. And I proved this in my other class, Calculus for STEM majors, using the formal definition of limits. And so we could do that, but I'm going to use what we learned yesterday or Tuesday in order to derive this. And this is how your book derives this. Okay. Actually, they first derive, and it's weird because the other way first derives this, but we're going to first actually derive the other one. Okay, so we're going to let f of x equal our logarithmic function, log base a of x. And we want to find the derivative f prime of x. Let's go through and let's actually rewrite this. Let's rewrite this in the using the definition of logarithm, what this actually means, right? This says take our base a, raise it to the other side, f of x, and that is equal to whatever you were taking the log of, in this case, x. So I'm just rewriting this using the definition of logs. So it's just meaning the same thing, just rewritten differently. Now let's take the derivative of both sides. So if I do that, and I could just rewrite it like that, d dx of this a raised to the f of x is equal to d dx, and the derivative of x with respect to x is easy. Okay, I just stated it up here. If we're taking the derivative, we're going to look at of an exponential piece, which is a raised to the f of x power, or a is raised to the x in our case. We look at the natural log of our base. So in our case, this is a natural log of a times the original function but we're not sure that f of x is just equal to x here. F of x is some function. We need to use our chain rule. And so we have to take the derivative of that inner piece, which is f of x. So times f prime of x. This is equal to the derivative of x, which is just 1. We're trying to find the derivative of f of x. Notice that in here, we now have this equation. We have this f prime of x in here. And so we can manipulate this and get f prime of x by itself, and we'll have our formula. So let's just divide both sides of this equation here by this piece, the natural log of a all times a raised to the f of x power. Do something to one side of the equation, we can do it to the other. That's what we're doing. And so we find then that the derivative f prime of x is equal to 1 over the natural log of a all times a raised to the f of x. Okay. But we need to go a little further. And what is f of x? So let's go back a little further because we're not quite done. Up here, f of x, remember? F of x is just log base a of x. So let's rewrite that. So this is equal to 1 over the natural log of a raised to the f of x, which was just log base a of x. Well, rules of logs and exponentials, these are the same base. Our bases are going to clear each other out. And so this is actually just equal to x. So we have 1 over natural log of a times x. And a lot of times you're going to put that x in front because it's, if you have a natural log, it's kind of hard to see. Is that x with the natural log? But it's not, it's times. So we would write it as 1 times 1 over x times the natural log of a. So that's the derivative of log base a of x. So to get the natural log, that formula there, and that's 1 over x, all we have to do is, we know that if f of x is equal to the natural log of x, this is equal to log base e of x. And so our base here is e. Our base here is e. So by this rule, the derivative of the natural log of x is equal to 1 all over x times the natural log of e. Well, natural log of e, you should know what that is. Again, if it helps you, this is log base e of e equals what? So this is saying, what is our exponent that we're going to raise our base to e to get back e? Well, we would raise e to the first power to get back e. So this natural log of e, log base e, natural log of e, log base e of e is just 1. So this is equal to 1 over x. So that is our other rule. The derivative of the natural log of x is equal to 1 over x. Okay. The thing is that maybe it's a natural log of some function, not just x. And so let's look at that. We can derive those really fast by using the chain rule. So again, the chain rule says, let's say we have y is equal to f of some inner function g of x. Again, the chain rule says to take the derivative of y, we take the derivative of the outer, y prime, of the inner, g of x, times the derivative of the inner, g prime of x. So if we have this y is equal to, let's say, let's start with the natural log, that one's easier, the natural log of some function, let's say g of x in here. This chain rule says we're going to take the derivative of the outer. So the outer function is the natural log. Natural log of x, we put 1 over x. So we're going to put 1 over the inner function, but our inner function in here is g of x. Times, though, the derivative of the inner, and the derivative of the inner would be g prime of x. So we can say that the derivative of y equals, maybe I'll write it this way, the derivative dy dx, or d dx of the natural log of g of x. This is the same thing as the derivative of the inner all over the inner. We'll be using mostly natural logs and base e when we're dealing with exponentials, but there are times when we're using other bases. And so let's just write using the chain rule, let's do that same thing for if it was log base a. So if we had y equals log base a of x, dy dx, the derivative of y, or y prime, different ways to write this. This was 1 over whatever natural log of whatever our base was, a, times, where is it at? The inner. Oops, but I wanted to write this maybe as g of x instead, not just x. So let's call this g of x. So times that inner. But then we had to multiply, because we're chain rule, the derivative of the inner, so g prime of x. So we can leave it like that, or we can clean it up and just put the derivative in the numerator there. So the derivative, so d dx of the log base a of x, or a of g of x, is equal to g prime of x, derivative of the inner, all over the natural log of whatever base we were using, in this case a, times g of x. You might see the g of x in front of there. Again, same reason as I was stating before. Okay, so I think we have now all the tools to go through and start taking derivatives of functions that have logs in them. So let me show a couple examples. Okay, so we're going to find the derivative of logarithmic functions. And our first example is y is equal to the natural log of -4x. And so I know that this is base e, and the derivative I'm going to have to look at, I probably should have that formula right there, but it's 1 over dy dx is 1 over whatever we're taking the natural log of, which in this case is -4x, times the derivative of the inner. So times d dx, if I take the derivative of negative 4x. So the derivative of y with respect to x is 1 over negative 4x, and the derivative of negative 4x is just negative 4. So we can cancel like factors in the numerator and denominator. We can do that because it's multiplication in between the negative 4 and the x. And so this is just equal to 1 over x. So what if it had been the natural log? So let's say y is equal to the natural log of parentheses 1 plus x cubed. So again, we're finding the derivative. So we can write that a little differently. We could write it as y prime if we wanted to. So this is equal to, so the outer function is the natural log, so it's 1 over whatever you're taking the natural log of, which in this case is 1 plus x cubed, times the derivative of the inner. So times d dx of 1 plus x cubed. So the derivative of y is, well, the derivative of 1 plus x cubed. Well, derivative of 1 is 0, and the derivative of x cubed, that is 3x squared. All over our denominator. And our denominator was 1 plus x cubed. So here's a case where if we use properties of logarithms, it could actually be a little easier to take the derivative. So let's look at the following. We're given that y is equal to the natural log of the square root of 2x plus 1. Again, we want to take the derivative of that. Well, I know that when we take the derivative, we first need to rewrite that square root without the radical. And so we can do that. Equivalent form would be the natural log of 2x plus 1. And that 2x plus 1, that whole thing is raised to the 1/2 power. So I could go ahead and I could take the derivative now. But if I do that, I'm going to have to use the chain rule, and I'm going to have to use the chain rule within the chain rule, actually. But if I take the derivative, I use my properties of logs, and I bring my exponent down first, I can rewrite it as y equals 1/2 the natural log of 2x plus 1. And so now it'd be easier to take the derivative of this. So this would be y prime equals, well, we just leave our coefficient alone, and we take the derivative of the natural log of 2x plus 1. So the outer natural log, we take 1 over, so times 1 over what we're taking the natural log of, which is 2x plus 1, times that derivative of the inside, d dx. 2x plus 1. So we get y prime is equal to 1 all over. I can think of this as 2 times that denominator, 2x plus 1. And that derivative of 2x plus 1, let's just put that in the numerator. Derivative of 2x is 2, and the derivative of 1 is 0. So I can simplify this a little bit. I have a 2 in the numerator, 2 in the denominator. Those cancel out. So I get my derivative is equal to 1 over 2x plus 1. I want to show this because maybe you didn't see that rule or you don't remember that rule of logs and you had to go about it without using that rule. So let me just show you how much more difficult it would have been if we didn't see that rule and didn't rewrite it. So we have seen in the past with taking derivatives, sometimes rewriting what we're taking the derivative of first in a different form can make our life a lot easier. So let's look at y equals the natural log. We would have had to rewrite it anyways from this point as this. So let's do that. So this is the natural log of 2x plus 1, all raised to the 1/2 power. Okay, so let's go and take the derivative now. So we have the derivative of our natural log. So our outer is the natural log. So we're going to put this 1 over whatever we're taking the natural log of. And in our case, we're taking the natural log of this whole piece, 2x plus 1, all raised to the 1/2, times the derivative of the inside. What color I want to use? So times the derivative of the inside. So let's just write that d dx of this 2x plus 1, all raised to the 1/2 power. So when I take the derivative of that inside, I'm going to also have to use the chain rule again. So let's just rewrite this. So far, what we have 1 over, well, this 2x plus 1 to the 1/2 power, let's just rewrite it as its radical. So square root of 2x plus 1 times, okay, so we have to use the chain rule again. And the outer piece is this thing to the 1/2 power. And so if I take the derivative of the outer, I would bring down my 1/2 of the inner, which is 2x plus 1, subtract 1 from my outer. So 1/2, let's just write it, minus 1, times the derivative of the inner. So times, I still haven't taken the derivative of the inner in this piece, d dx of 2x plus 1. So rewriting it, y prime equals 1 all over, I guess we'll leave it, square root of 2x plus 1 all times this piece. This piece right here is 1 all over that 2. Notice that 1/2 minus 1 is a negative 1/2 power. So I'm just taking 2x plus 1 to the negative 1/2 power. I'm going to rewrite it as 1 over that and make the exponent positive and rewrite it as a radical. So this piece is the same thing as 2 times the square root of 2x plus 1 times the derivative of the inner. So the derivative of 2x plus 1. Well, derivative of 2x is just 2, and the derivative of 1 is 0. If you want to put that over 1 to help you see it, you can. I notice this is all strictly multiplication in the denominator. So I can simplify this 2 out here, this 2 here, with this 2 up in the numerator. So this would equal 1 all over, well, square root of 2x plus 1 times square root of 2x plus 1. That's square root of 2x plus 1 quantity squared, which cancels the radical, giving us that 2x plus 1. Which is the same thing we got over here, but so much more complicated because we didn't rewrite it first by bringing that exponent down. So here's where rules of logarithms can be really helpful to rewrite, if we have a logarithm function that we're going to be taking the derivative of and it's complicated, rewrite it in a simpler form and then take the derivative.